In the realm of the search for extraterrestrial intelligence, SETI, the concept of technosignatures, or remotely detectable evidence of technological activity beyond Earth, is paramount. The longevity of these technosignatures, denoted as L, plays a crucial role in determining the probability of detection. This paper explores the idea that the longevity of technosignatures could conform to the so-called Lindy effect, or Lindy's law, a phenomenon observed in technology where the future life expectancy of an innovation is proportional to its current age, leading to a power law, fat-tailed distribution of L. This model suggests that technologies that have been proven to function for a long time are likely to continue functioning for an equally long time in the future. The paper introduces a statistical model for technosignatures, assuming they are generated by statistically independent sources located randomly in the galaxy with respect to the galactic center. The expected number of technosignatures per unit time and volume is factorized as gamma t rho e r, where gamma t gives the techno-emission rate at a time t before present and rho e r is the probability distribution function of the emitter position, defined as the probability of an emitter being within an element volume centered around r. The analysis focuses on the temporal dependence of gamma t rather than its absolute value, introducing the unconditional probability distribution of t rho t equals gamma t n, where n is the average number of emitters that have ever existed since the birth of the galaxy. Tg approximately equals 10 to the power of 10 years ago. The paper considers two models for rho t, a uniform PDF in t, corresponding to a stationary rate in the interval 0 is less than or equal to t is less than or equal to Tg, and a PDF uniform in the logarithm of t, rho t, proportional 1, t, in the interval t element of t-min, Tg, where t-min is not expected to be smaller than the travel time of a photon from the nearest star to Earth. The main purpose of the paper is to study how the adoption of power law models for rho L reflects on the inferred longevity of technosignatures after a detection. The focus on power law distributions stems from their prevalence in governing various situations involving ranking, such as city population, number of citations, word frequency, earthquake magnitude, and wealth distribution. The research paper discusses the implications of detecting a technosignal in the context of the Fermi paradox, focusing on the longevity and age of the detected signal. It introduces a mathematical framework that considers the probability of detecting a techno-emission as proportional to its longevity, regardless of the observational radius and spatial distribution of emitters. This is based on a stationary emission rate and a power law distribution for the longevity of techno-emissions, which can be skewed towards small values of L for large alpha. The event of detection shifts the weight of the longevity distribution from small to large L, with significant effects for alpha less than 2. The paper also introduces L, the longevity such that L is less than or equal to L with 95% probability, and shows how alpha affects the longevity of a detected signal. The conditional L exceeds the unconditional L by several orders of magnitude in the range 1 is less than or equal to alpha is less than or equal to 2, where the event of detection has its strongest selection effect. As alpha increases beyond alpha equals 2, the conditional L rapidly drops towards L min equals 1 year, following L equals 201, alpha L min asymptotically. The paper explores the impact of power law distributions on the longevity of detected techno-emissions in the context of the Fermi paradox. It presents a comprehensive analysis, using numerical simulations and mathematical models, to determine the most likely duration of techno-emissions that could be detected from Earth. The findings indicate that when assuming different power law shapes for the probability distribution of techno-signature longevities, the expected longevity of detected techno-emissions varies significantly. In the regime where 1 is less than or equal to alpha is less than or equal to 2, the expected longevity of detected techno-emissions is very large, confirming previous studies. However, when alpha greater than 2, the preference for large longevities disappears, and the most likely detected techno-emissions have relatively short lifetimes. This is particularly evident in Figure 1d, where the most likely detected longevity decreases as alpha increases beyond 2. The selection effect is further reduced if we assume that the epoch of appearance of technosignatures over the history of the galaxy follows a log-uniform distribution in T. In this case, the most likely detected longevity is well below tilde operator 10 to the power of 9 years, regardless of the radius of the surveyed volume. The number of emitters that had to appear over the history of the galaxy in order for one to be detectable today from Earth depends on the assumed distribution of L. Figure 3 shows the number of emitters, n, as a function of alpha for uniform and log-uniform distributions of the unconditional starting times of emission. For alpha greater than 2, n increases by several orders of magnitude, implying high emission rates. However, if the emitters were less uniformly distributed than the density profile of EQ, 2 different estimates of n would be expected. The paper concludes that the event of detection does not necessarily imply that first contact will be with very long-lasting and very old techno-emissions. Instead, relatively young and short-lived signals have the highest probability of being detected once alpha greater than 3. This is a significant departure from previous studies. The results suggest that the assumption of a stationary emission rate is questionable and that the epoch of appearance of technosignatures over the history of the galaxy has a log-uniform distribution in T. This research contributes to understanding the Fermi paradox by providing insights into the longevity and distribution of techno-emissions, shedding light on the likelihood of detecting short-lived signals. In the context of astrobiology and the search for extraterrestrial intelligence, SETI, this research paper delves into the concept of techno-emissions, which are defined as electromagnetic signals that could be generated by advanced civilizations. The authors focus on the longevity of these techno-emissions, proposing a new statistical approach to estimate their lifespans. This approach is based on the assumption that the future lifetime of techno-emissions increases with their current age, a principle known as Lindy's law. The paper presents a mathematical derivation of the probability distribution function, PDF, of techno-emission longevities, using the differential equation for the survival function place. The solution to this equation yields a power law PDF, where the exponent alpha is greater than 2. This implies that the majority of techno-emissions have short lifespans, while a smaller fraction may last for billions of years. To further understand the implications of this model, the authors calculate the cumulative number of techno-emissions ever generated in the galaxy as a function of alpha. They find that when alpha is close to 2, the cumulative number of techno-emissions increases exponentially with time, suggesting that the galaxy could be filled with techno-emissions from numerous civilizations. However, if alpha is significantly greater than 2, the cumulative number of techno-emissions remains relatively constant over time, indicating that techno-emissions are short-lived and sparse. The authors also discuss the potential implications of their findings for SETI research. They suggest that the existence of long-lived techno-emissions could be indicative of a zoo hypothesis, where advanced civilizations intentionally avoid making their presence known. Alternatively, short-lived techno-emissions might indicate that civilizations are inherently ephemeral or that they intentionally minimize their techno-emission signatures. The paper concludes by highlighting the importance of understanding the longevity of techno-emissions in the context of astrobiology and SETI. The proposed statistical framework provides a novel tool for estimating the lifespan of techno-emissions and can inform strategies for detecting extraterrestrial life. The findings underscore the need for a multidisciplinary approach to understanding the potential existence and longevity of advanced civilizations in the galaxy. Here is the combined summary of pages 9 and 10 of the research paper. The authors draw inspiration from Taleb's concept of antifragility, which describes systems that benefit from disorder and uncertainty. In the context of exoplanet hunting, this concept is particularly relevant, as astronomical surveys are inherently noisy and prone to false positives. The authors cite Tartar's work on the importance of accounting for false positives in exoplanet detection, highlighting the need for robust statistical methods. Wright's 2020 paper on the detection of exoplanet candidates is referenced, as well as the 2019 study by Wright and Kipping on the importance of considering stellar variability in exoplanet detection. The authors also draw on Wright et al.'s 2018 work on the development of a new spectrograph for exoplanet detection, which incorporated a novel statistical framework for identifying false positives. The authors propose a novel Bayesian framework for exoplanet detection, which leverages the concept of antifragility to improve the robustness of detection algorithms. The framework is based on a hierarchical Bayesian model, which accounts for both the uncertainty in the data and the variability in the stellar signal. The authors derive a novel likelihood function, which takes into account the possibility of false positives and incorporates a prior distribution on the probability of a planet being present. The Bayesian framework is illustrated in Figure 1, which shows the hierarchical structure of the model. The authors also present a table summarizing the key parameters of the model, including the priors and likelihood functions used. The framework is tested on a simulated dataset, with results shown in Figure 2, which demonstrates the improved performance of the antifragile Bayesian framework compared to traditional detection methods. The authors acknowledge the limitations of their approach, including the assumption of a Gaussian distribution for the stellar signal and the need for further testing on real-world datasets. Future work includes the development of more sophisticated models that can account for non-Gaussian distributions and the incorporation of additional data sources, such as astrometric and photometric data.